Hello hackers, what the heck is going on? Now as you can see, there's some new updates to the hack. There's a shiny new crystal oscillator, and I will quickly go into why that is there. But there is also some wiring changes on the motherboard to facilitate this new crystal oscillator. And I'm going to announce that this series is going to be named Hack News, like tech news. Wait, now I'm thinking about it. Is the word hackology good? Well, leave a comment below whether you think that's a good word or not. So, let's go into the motherboard. Now, the original plan for the USART actually used the CPU clock divided by 2 using the 74LS74 D flip-flop to become like 1.79 MHz. This is not a multiple of any common used baud rate, but I think I can just route that through the programmable timer to get something close enough. Through my calculation, I can get something like within 1% of a common baud rate. But it's going to be very slow because you need to divide by a large number to get the wiggle room of the last few digits to just adjust for the error. But the main reason I don't use like a separate oscillator is that originally I don't actually want to operate an asynchronous bus on this motherboard, because when you go into the asynchronous bus, then you are operating things at different phases, you will operate things at different speeds, and if they don't line up, they will cause random problem. And it will be very hard to debug. But when I read the data sheet of the USART carefully, I find out that this is basically an entire system of its own. It communicates with the CPU actually using an asynchronous bus already, and the clock for that is only for reference of the USART of the serial port. But then I just decided, what the heck, and went on with the asynchronous bus. So I added this crystal oscillator here and wired that up to the 8253, like the programmable timer, and wire the output to the receive clock and transmit clock to the USART, the universal synchronous and asynchronous receiver and transceiver. So that's it for the board. What else? Well, this part may disappoint you, because if you remember that tip of the iceberg meme image, now the tip, or the shiny part, is all the exciting part regarding designing a computer. Selecting the CPU, selecting graphics, selecting like a glue logic, like determining how much RAM it's going to have, make the memory map, like how much ROM, what it will include, what operating system it will support, and basically you can brainstorm all day and the outcome will always amaze you. But the bottom part, the bulk of it, the majority of the development is the boring work, like really actually going into the circuit and lay it out on the PCB, like actually trying to push it on GitHub so that everybody can see your design, because this is an important part of the hack. I'm going to share this design to others so that others can make compatible product. Like compatible product is the key word here. If I'm going to win whatever the 8-bit computer race in 2022 is, but if I'm going to make a successful product, I need compatible clones. Like if I'm IBM, I need the Compacts, the HPs, the ASTs, the Dells to make HEC popular. And there's the software part. You see, I've stacked an enormous, ridiculous amount of sockets on this ROM. And that's because when I pull it out, I can avoid hurting the original socket by pulling out and putting in the ROM a lot of times. But this will be over soon because this is a lesson I learned from a previous project. And this time I set the ROM to be flashable. So theoretically, when I got a basic like system Monica running, I can connect the computer through such a USB to serial connector to the HEC and actually use just a regular cable to transfer the ROM content onto the computer, temporarily store it on like a piece of RAM, and then the program will flash it to the ROM and reboot from the updated ROM. This is just like updating the BIOS on a motherboard, and this will actually streamline the development process by a lot. So I'm hopeful to actually see the development accelerate. And the third part of the video is an announcement for a future mini-series, or not actually a mini-series, but it will kind of be a big series, where I will discuss all aspects of the HEC with the end goal of, if you watch all those series, you will gain enough technical detail knowledge to build your own HEC clone. Because HEC is not only about the Z80. It's not only about the peripherals. You can actually swap out the peripherals if you make the software layer compatible. It's not about the memory map. It's not about the I/O map. These are the things that, when you think about compatibility in 8-bit computers, these are the things that pops into your mind. When you think about, oh, I want to make something like a Famiclone, I need to make the PPU at its place, I need to make the ROM and the RAM, like everything in its right place, right? But for the HEC, it's not important. It's more about the protocols to communicate, the bus structure, like the drivers. If you can get those correct, you can make your HEC computer even with an entirely different CPU, entirely different physical memory map. It generally doesn't matter. But the protocols and stuff, if you are not familiar with it, it's going to be a little bit more complicated than just putting the peripherals at the right address. Because it involves in like reading specific address to get like what kind of a device this is, reading a specific address to obtain like what driver you should use for it, and all that kind of stuff. But I mean, this is like the 8-bit computer evolved. It's like the next level of 8-bit computers. So it should be expected, actually. Yeah, but I think that's it for today's HEC news. I will see you in the next video.